everyone, and welcome to Control Automation Day 2026. My name is David, and I'm the Director of Engineering Content here at Control.com. Every year for our session at this event, we try and offer some sort of hands-on demonstration. That's a solution to some sort of problem that's facing industry, or a tutorial that teaches you how to get started with some basic project of your own. But this year, we're going to take a look at a problem that seems to be getting worse year by year. It's not that we're facing a lack of complete solutions for an entire automated system in industry. The problem is actually the exact opposite. A lot of times when you go to a trade show or you read literature online, go to visit a manufacturer's website, what you see is a solution that is a one-size-fits-all that answers or solves every problem that you could have. This has become even worse since the discussion of data took over. Now things are less about control of the actuators and the sensors and the devices around the industry and the facility floor, but instead it's about the flow of information, how it comes to and from not just the control system, but levels of SCADA above that, and now analytics and AI. So since data has taken over this conversation, now everything we see is about how to get that data to move properly. Why is this such a big deal? Well, it's essentially because without information, we can't make any decisions. All the decisions that we make are honestly around saving money, whether that's decreasing downtime, increasing efficiency and throughput in a system. It's all about making more money in the end. And we have to have information to be able to complete this flow. Well, over the years, we've gotten really good at making the logic part of the system, the control part of a control system, very effective. So now we're faced with this data flow challenge, and how do we get it to work? Well, as engineers, we often tend to look at the ground floor implementation, basically asking the question of how do we get access to that data? And this is where we run into that problem of the one-size-fits-all. The solutions are where it can answer the problem for every industry and every application. And I suppose that could be true, but we skeptically look at that and say, but how does that fit for my situation? So in today's talk, I'm going to split this up into four different families, four different categories of how we can implement data flow throughout a system to be able to bring that information from the sensors that are down at the ground floor all the way up to the systems that are stored in a local server or even in a cloud system online. But first, before we get started with looking at those four categories, we need to get started with understanding what are we talking about with control system. What are the common elements? And many of these will be very familiar to all of you. What are those elements that make up a typical control system? So that's where we're going to start. Let's have a look at a representative control system and all of its parts. So that then, as we add in these different categories of implementation of data flow, they will start to make more sense in the context of a complete automation system. So let's get started with what that traditional control system looks like. This is representative of a normal industrial control system. You might find this inside of a cabinet, but we've just removed the subpanel to be able to give an illustration of each one of the necessary parts. So up here we have the power supply section, power supply and breaker. It's not necessarily part of the control system, but it's necessary for the control system to be able to work. Here we have a PLC. Inside a cabinet, we might find any brand or any make and model of PLC. This one just happens to be a Mitsubishi FX series. We have networking equipment, a switch in this case. And that switch distributes our network to the other peripheral devices. So here we have a remote I/O, which has a couple of I/O devices. These are sensors that are attached to the things that the motor is driving, perhaps a conveyor system. This is a VFD, and inside a cabinet, we might find multiple of these VFDs. Here we also have a robot, which represents either the robot kinematics or a motion axes, which PLCs are often found running. So this constitutes a sample system that's equivalent to how a normal network, a normal industrial control system inside of a cabinet would look. So back to the problem of getting data out of the PLC. We know that the PLC is the central controller for the process. It has been for decades, but we want to somehow extract the critical information from it without disrupting the process. And there's a real challenge. We can completely change the control system, and there are solutions that can do that, but without disrupting the control system, there are some limitations. So when it comes to the IoT, that's a buzzword that we hear a lot. The IoT is something that stands for the Internet of Things. It became popular when sensors and basic actuators were exposed to the internet, hence the Internet of Things, meaning anything that can be given access to the internet through some sort of portal. People were able to log onto a website and change the music or the colors of Christmas lights in somebody's house remotely, and all sorts of these experiments that prove the power of data connectivity. We can collect that data. We can analyze that data. Now, when we move to an industrial setting, you can see the obvious security risks of allowing somebody to come in and access the actuators inside of a facility. So this concept of the Industrial Internet of Things, or IIoT, builds in an inherent sense of security. It's still not typically the best way to describe what we're doing, IIoT. So sometimes you'll see that language, but often now it's being overtaken by language that it pulls it into a SCADA system. A SCADA system that can either be stored remotely or locally in a facility, just like it has been for decades. But since the IIoT is built on a layer of industry, the trick is we want to be able to use those same classic industrial protocols to gain access to the data. The protocols that PLCs and other controllers have been using for decades. If we can somehow use devices that can get access to those protocols, get the critical information, and then expose it securely to a place on the internet to be able to store and analyze that data, we begin to see this data flow. Now, again, it can store it locally or securely transported to a cloud system, but many facilities prefer to keep all of that sensitive information in-house for good reason. But regardless of which of those routes we choose, there are some common protocols that IIoT and IoT in general have created around the world that can help us use that a little bit better. For example, MQTT. MQTT is a protocol that was originally designed to be able to take any kind of information and send it through a broker, which is something that assigns names and which direction the information is going and other critical information to be able to share it with a database that can store that information. No matter where it's going, that's our goal, is to be able to take it from our local control system up to a higher control system to be able to analyze it. And now that AI has become so powerful, we can use AI models to begin to process that information. Can we find anomalies? Can we look at patterns? Can we figure out some trends where we might be able to either cut down on maintenance, optimize machines a little bit better? All of those models are being continually developed, but they depend on that data to be able to succeed and accomplish what they're designed to do. So first, we are going to look at our most basic, simple IIoT model. So here we can see our control system just like before, but we've added in orange in our diagram a gateway. Now, a gateway's objective, a gateway's goal is very simple. It converts from one protocol to another. Now, a gateway can often convert from one network to another, like a local network in a facility or in your house, to be able to expose that information, whatever information is important, to the internet as a whole, or just to some higher level of a network. In this case, we can use a gateway that taps into the PLC. That PLC is able to send data when the gateway requests it, and then the gateway converts it to a protocol like MQTT, OPC UA, or REST API to be able to transfer it to a database as our IIoT protocols are meant to do. So as we can see in this system, the PLC is still controlling the process, but we're accessing the data from the gateway. Now let's take a look at a physical demonstration of this system. To be able to implement the most basic IIoT setup, we have to add something onto the PLC to be able to extend its ability and allow that MQTT communication. So here what we'll be showing is a gateway. This gateway is a Stride gateway that connects through a Modbus communication back to the PLC. Modbus is extremely common for these legacy gateways because so many old PLCs over the decades have made use of Modbus, either Modbus TCP, Modbus RTU, Modbus ASCII. And for all these protocols, they have a very standard way of being able to address coils and registers. Since it's so consistent, we know that we can count on one of these for almost any legacy control system. So we can connect this and apply it, give it power by plugging it into the terminal block, turning our system on. Now, in the case of this, which is Modbus RTU, we would use a twisted pair wire to be able to connect the send and receive to the respective receive and send headers on the PLC. Lots of PLCs have these headers on the top or sides to be able to connect Modbus protocols to, RS-485 or RS-232, depending on the specific setup. So in this case, I'm going to just illustrate, and I'm not actually going to make the connections and configurations today, but we would connect the ends of our twisted pair to the send and receive and the send and receive. Then we would be able to request information from the right registers or coils, which represent bits or integers of information, and relay those through MQTT up through the network to our enterprise level and be able to store those on a local or remote database. Now, as we've said before, being able to connect a device directly to the enterprise network and then have it connect to our PLC setup presents some security risks, and certainly a discussion with an IT department. And sometimes those are going to require a little bit more investigation and a little bit more work. So there are definitely pros and cons to this, but it's a great solution for legacy systems that do not want to risk interfering with the control and only want to have a simple hardware setup somewhere nearby. As with any system, there are some pros and cons to looking at this basic IIoT model. This one's great for legacy systems because, in our example using Modbus, the Modbus protocol goes back many decades, so most PLCs would be able to communicate with this gateway, and we can install it beside the process without affecting the process. But of course, there are some cons, some negatives to this process. The first is we need some extra hardware that needs to be configured. In this case, the gateway, it's not really expensive, but we do have to add in that hardware somewhere into our system, taking up some real estate in a control cabinet or adding it onto a platform somewhere nearby. There are also some possible security issues. As with all protocols, the developers and maintainers of these systems are completely aware of vulnerabilities, and they're constantly working hard to address them. But still, there are security issues anytime a network is able to have access to your PLC. And if possible, we either want to avoid that or minimize any of those risks. So this basic IIoT model may not be a right fit for everyone. So now, how can we fix at least the issue of the extra hardware? Instead of having to add in this extra gateway and use wires to connect it over to the PLC, what can we do instead? So next, we're going to take a look at a model that's called the integrated IIoT model. So as we can see in our diagram now, the gateway has been embedded inside of the PLC. This really is quite similar to the MQTT gateway that we looked at before, but instead of being connected to the PLC through an external hardwire setup, it's able to share that data automatically because it's been built or baked right into that PLC. So we call it integrated. Just like when I/O modules are included right on the PLC itself, we call them integrated I/O modules instead of extra or remote or modular types of setups. So in this case, we've included the IIoT setup right into the PLC. Not every manufacturer and model does this because, again, there are some security disadvantages, and not everyone feels comfortable, for good reason, connecting their PLC directly to a network that can be exposed to the internet. Now, addressing security, there are plenty of SSL and TLS encryption protocols, and there can be strict authorization placed when any computer is trying to access a publish or subscribe topic, which is the way MQTT distributes its information. Now, let's take a look at the second scenario, the integrated IIoT scenario, in a hands-on demonstration below. For the next demonstration, we'll show how one of these integrated IIoT with a gateway built right into the PLC, how one of those can be connected. Now, if the PLC does not already contain that function, it does mean that we would have to swap out the PLC for a different one. That's no small change. So it's only approachable if you're either designing a new project or you're willing to put your project onto a new PLC that has that function. But especially if you're designing a new project, this may be a really easy way to go. So here we have a PLC, a BRX PLC from Automation Direct, just a representative example of one that has that functionality built into it. So we are going to disconnect our PLC from power and from the network and remove it from the system. And in its place, we are going to install the new PLC with MQTT and a connection to our network and apply power. And now, as you might observe, this network connection is going directly to our factory level network. So to be able to communicate with a remote or local database, we have to use the remaining port on our switch to be able to connect to the enterprise level network. This, again, is where those security risks come in of being able to directly connect to the factory network from the outside world. So here again, we have that discussion with IT and the necessary security risks that the cautions that need to be taken in order to protect that network. It's a very important topic of discussion these days. To be completely sure about security, we do need to consider the idea of isolation. Making a completely separate network that never has to talk to the PLC or the other devices on your network is really the only way to ensure 100% security in your system. There is an IIoT model for being able to accomplish this, though. So let's take a look at our third scenario. In this model, which is what we call the separated IIoT model, we have no control, only sensing. So when we think about the flow of information going two directions, as it does in a PLC, we read information from sensors, but we also send information out to actuators, motion axes, things like that. In the separated IIoT model, we are only looking at the collection of information, sensors only. So there's now some complete isolation from one network to another. This remote I/O module cannot see the PLC network or the motion axes or the robots at all. There's zero risk of unauthorized access to the network. So it's an upside, but there's also a downside to it in that this does require a lot of extra hardware. Extra sensors, because we cannot connect to the sensors that are already fed into the PLC, extra network devices, and the gateway must be external to the PLC and its network. So there is a lot of extra hardware. So now let's take a look at this separated model here in real life in this demonstration. So for a demonstration of how we would set up the separated IIoT network or isolated network, we're going to move this over and give ourselves just a little bit of extra space over here on the side, clear our bench, and we're going to bring up an example of a device that uses both data collection, because it has sensors attached to it, and one with MQTT or some sort of IIoT protocol ability built right into it. Now, since we have extra sensors that were not a part of our system, this is completely isolated, and when we said it requires extra hardware, this is what we're talking about. All of this has to be installed alongside the existing I/O devices. So if we want to measure the position or speed of a belt, the position of objects, or the temperature, vibration of motors, we have to choose the appropriate sensors that we can install alongside our system. But once we've made this change, we can connect it to the external network, not to our factory level network. So we've removed any risk of influence of somebody being able to come in and affect the factory level network. And we apply power. And after a few seconds, we see in this isolated network, completely separate, we have power for all of the devices and for the sensors. So finally, what if we want to avoid having extra hardware and we want to address any of those security issues that were brought up earlier? This is finally the most complex solution of all, but it's probably the most flexible and the most able to be secured. So what is this one? In this model, we rely on an industrial PC. Now, an industrial PC acts and behaves much like a computer, except that it's industrialized, which means the case is more rugged, it's able to withstand higher temperatures, usually has no vents to keep dust and moisture out, and it has ports that are specifically designed for industrial protocols and often for local I/O points and even I/O modules attached alongside. From the outside, it looks much like a PLC, but on the inside, some of the major differences are that it contains an operating system. Now, in a PLC, we can only read information, perform logic, and then send that information back out to output terminals. Sometimes we have a separate function that can upload data through MQTT. That's a solution that we discussed earlier. But our ability to expand and add other applications onto a PLC is quite limited. In an industrial PC, we don't have that limitation. One of the problems, though, is that it requires a higher skill set of computer operation to be able to understand what's going on in the background of a PC. So it becomes more of a blend of the electromechanical skills and the computer operation skills. But what benefit do we get from introducing an actual PC into our operation? It's that we can put the security protocols that are standard to any computer that can connect to the internet right onto our factory level network. So they can be updated, they can be maintained regularly, and we have access to whole sets of tools that otherwise wouldn't be available in a PLC. We also have much more flexibility when it comes to the applications. So we can connect to industrial protocols, but not just a limited set, a virtually unlimited set, through the ability to install what we call containerized applications. Containerized means that each application or each program runs inside the operating system, and it can share the data that it requires and data that it gains and uses with all of the other applications inside the PLC. So our logic for actuators and buttons can be running in one container, motion instructions can be running in a separate one, and our IIoT functions can be running in a third container, and each of them can seamlessly share data, but it's designed with the security to keep our data safe, but also the processing power to make sure that we're not lagging down the system like we would if we were trying to do all of this inside of a PLC. And since it's a computer, we can even install some of the basic processing, the data handling inside the IPC, rather than having to hand it off to another system, analyze it and make decisions, and then send it back through the network to the IPC. So it's becoming a much more powerful way to be able to accomplish a lot of steps all in one. So now we're going to go to what does this physically look like to install an IPC or this industrial PC inside of a real control system. So for our final scenario, we're going to take a look at this, how to install this industrial PC. Since it's a computer, you might think that adds a little bit of complexity. However, industrial PCs or IPCs are built with the industry in mind. So here's an example. This is a computer from a company called OnLogic. They make a lot of these industrial PCs, and as we might know, there's a lot of headers that look like industrial headers for connecting I/O devices, but it also has more familiar computer connections. Ethernet ports, USB ports, an HDMI port, USB-C for configuration. It also, instead of running on the normal computer power supplies, they're usually designed to run on the 24 volts that we already have from our cabinet. So we're going to remove power. We are again going to remove our controller, our PLC, from the situation. And install our IPC in its place. These IPCs are usually built on top of a Linux or a Windows operating system. And the nice thing about an operating system is, instead of a PLC, which reads information, executes logic, and sends instructions to outputs. It's very efficient at that. But with an operating system, we can install applications that can share data between all of the functions, like motion control, motor drive analysis, all of the network security options, being able to even install our own custom scripts that can use AI algorithms to be able to analyze the data. So if we want to perform some basic predictive maintenance or look for anomalies directly on our controller, that's possible. With the processing power and speed of these, we can have one part that's devoted to the control system, but we can have another part that's devoted to these different functions, but they can still share data across a layer on the operating system. So while the complexity is much greater, granted, for these devices, it takes a little bit more skills, not just in the electromechanical that we've been used to, which covers all of this area, but also computer skills. We certainly need to learn a little bit more in that scenario. But these operating systems that are built onto these industrial PCs or IPCs can be a great way, can bring our control system into the future with flexibility, but they're still designed to be able to support the protocols, the voltages, the rugged environments that are demanded of these industrial applications. Now, to conclude this discussion, let's take a look at those 4 different ways that we've discussed to get data. The basic IIoT method simply uses a gateway to convert a legacy protocol like Modbus RTU into a modern IIoT protocol like MQTT to be able to hand off the data. Benefits, but also some security risks. The next setup was IIoT directly embedded into the PLC, the integrated solution. This is much less hardware intensive, but it still contains some of those security vulnerabilities that we've discussed, and so many manufacturers prefer more advanced methods or isolation. Speaking of isolation, that brings us to the third method, where the IIoT gateway exists with access to sensors in a completely separate, isolated network only for data collection. Now, to address both the security and the extra hardware, we move to the IPC system, the industrial PC, where the controller acts with logic, and it provides the gateway for IIoT communication, but it also provides some of our basic data processing and handling right there on the IPC. A more complex process, no doubt about that, but it's certainly very important to learn as industry moves in that direction. It's always important to ask questions and learn about those things that you don't understand, because as we say around here, never invest in anything if you really don't understand what it's doing. And that rings true in control system technology for sure. So thank you for taking the time to watch this short demonstration. We will have time for a Q&A after, but we may collect some of these questions to confer with other experts in the field and direct those answers to those experts to be able to provide a more complete solution, especially if yours addresses a particular scenario. So we invite the Q&As, stay tuned to listen in, and as always, keep building awesome stuff. Thanks for watching.
All right. Well, thank you, David, for that presentation. I know I always learn something new from one of your demonstrations. Love the hands-on stuff. So we already have several good questions, but there's still time for our audience to submit your questions. I do want to address the first one in the queue is asking about there being any documents to read or something to go back and watch this. It will be available on demand, and also in the handouts tab now, you should be able to see some of the slides that David shared. So with that one out of the way, we will jump to the other more detailed questions. Let's see here. So first one here, are IPCs, processors and inner circuitry different from normal PCs?
Yes, very much so.